Hi everyone, today we're going to be talking about solving linear systems by graphing. That is our learning target for the day, and this is Algebra Chapter 7, Lesson 1. You can find this lesson in your textbook on pages 427 and 428 if you'd like to read the lesson ahead of time, or if you'd like to refer back to the lesson later on and look at some more examples and exercises. There is the key vocabulary: system of linear equations, solution of a system of linear equations, and then consistent and independent system. Here's an example of a linear system. Notice it has two equations. So that's our goal for today. How does this lesson fit into the bigger picture? There are several methods that we're going to be learning to solve linear systems in Algebra 1. First of all, in Algebra 1, we're only going to be dealing with 2 by 2 linear systems, and we're going to be using graphing, substitution, and linear combinations or elimination methods. So 3 different methods we will learn to solve linear systems in Algebra 1. As you move into Algebra 2, you will review those 3 methods that you learned in Algebra 1, and you'll add some new methods, including using matrices, reduced row operations, Cramer's rule, and applying linear systems to linear programming problems. You'll also be solving 3 by 3 linear systems, which include 3 equations in 3 variables. And beyond that, you're going to be solving multivariable systems, and that's coming soon. So if you take a look at your textbooks, Lesson 7.1 talks about solving linear systems by graphing. So prior to this, you've already learned how to graph a linear equation, and now you will graph and solve a linear system so that you can analyze costs of a season pass to a recreation club. There's a real-life application why you would want to know this. So you do have a notes page on your desk, I hope, because I handed that out before you went home today, and I'm hoping that you're using your note-taking guide to answer these questions today. And after watching this video or during the video, you should find the answer to these questions. We're first going to define what a system of linear equations is. We're going to explain how to solve a system of linear equations. We're going to identify what the solution is to a system of linear equations, how many solutions could exist, and determine how you would know if a particular point is a solution to the system of linear equations, and explain how you would know. So have that note-taking guide handy so that you can write down some answers as you watch this video. So a system of linear equations is simply 2 or more linear equations in the same variables. An example is shown below. Notice how we have 2 equations and they both have x and y in them. The solution of a system of linear equations is an ordered pair that satisfies each equation in the system. So your solution will look like an xy pair. As we said earlier, one way to find the solution of a linear system is to graph both lines and look for the intersection point. If the lines intersect in a single point, then the coordinates of that point are the solution to the linear system. This is called the graphical method. So notice we have 2 linear equations, and then we have the graphs of both of those equations, and you can see that the intersection point is right about there, and we could actually read the intersection point here, and it would be 3, 2, and we would want to put that point in parentheses and label that as the solution. So the solution to that linear system is 3, 2. Now, you can check your solution algebraically by plugging in 3 for your x value and 2 for your y value into this equation over here, and it should turn out to be a true statement. And you could also plug in 3 for x and 2 for y on the second equation, and it should turn out to be a true statement. We will do that in the next example. There are several different types of linear systems. In example 1, when there is exactly one solution, as we just saw, the linear system has exactly one solution, is called a consistent independent system. So down here, you will see an example of a consistent, independent system. The lines are distinct, they are independent of one another, and they intersect, so they are called consistent. You will solve consistent, independent systems in the first 4 lessons, and then in the 5th and 6th lesson, you will solve other types of systems. Other types of systems could be consistent, dependent systems or inconsistent systems. Those are coming soon. Why do you need to know how to solve linear systems? Well, solving these types of problems helps us determine in real life situations whether or not we should buy a season pass, join a club, pay for membership, or whether or not we should just pay the weekly or monthly or session fee. So here's an example where as a season pass holder, you pay $4 per session to use the town's tennis courts, but you buy the season pass for $90 up front. If you decide not to buy the season pass, you pay more per session, $13, to use the tennis courts, but you do not have to pay the $90 upfront fee. So the system of linear equations would help you to determine whether or not you should pay for a season pass. We are going to come back to this problem and solve it in the future. I just wanted you to see how you could use this in your real life. Okay, so how can you tell if an ordered pair is a solution to the linear system? Remember that an ordered pair has an x and a y. And the x value is the first coordinate and the y value is the second coordinate. So in this particular linear system, we have what we think might be a solution, 4, 1, and we have to check it to see if it works. So what we're going to do is we're going to plug in 4 for the x and 1 for the y into both equations to see if it is indeed the solution. So in the first equation, we plug in 4 for x and we plug in 1 for y, and we end up with 4 plus 2 times 1 is equal to 6. And the little question mark is there to determine, is it a solution or not? Is that a true statement or a false statement? And hopefully you can see that that is true. So we're going to write that that's a true statement. And then when we look at the second equation, 3 times 4 is 12. We plug in the 4 for the x and the 1 for the y. 12 plus 1 is 11. Is that true? Hopefully you can see that statement is false. And so because that is a false statement, in order for this to be a solution to the system, it has to be the point that satisfies both equations. And so this ordered pair 4, 1 is not a solution. And so we're going to write that in. Not a solution. And the reason it's not a solution is because it doesn't satisfy both equations. Okay, next example. We're going to use -2 for x and 1 for y, and we're going to substitute or evaluate that first equation by plugging in -2 for x and 1 for y to see if it's a true statement. So -5 times -2 is -10, and -10 minus 2 times 1 is -12. That turns out to be true. And when we plug in -2 for x in the second equation and +1 for y in the second equation, we get -2 plus 3 times 1 equals 1. That also turns out to be true. So since we have 2 trues down here, we say that -2, 1 is a solution. So this one is a solution, and the previous one is not a solution. Your turn to try. Pause the video right now and write down your answer to number 6 on your note-taking guide. Be sure to show your work or explain your reasoning. Please hit pause on the video right now. Next, we're going to actually learn how to solve linear systems by graphing. So to identify the solution to a linear system that is already graphed, and then we're going to prove algebraically that your solution is correct. So here we have a linear system, which is 2 equations graphed on the same set of axes. And notice we do have an intersection point right here. And basically all we have to do is identify what that solution is. So what I'd like to have you do is circle that point of intersection whenever you see it. That tells me you know exactly where it is. You know where to look for it. And then read the coordinates of that point of intersection. And you can see that the solution is 1, 3. X is 1, y is 3. And then we're going to verify or prove algebraically that our solution is correct by plugging in 1 for x and 3 for y in both of those equations. So in the first equation, we get 3 equals 5 times 1 minus 2, and that turns out to be true because 3 is equal to 5 minus 2. In the second equation, we plug in 1 for x and 3 for y, and we get 3 equals negative 1 plus 4, and that turns out to be true. And basically what we've just done is we have verified the solution that we found on our graph. And the reason why you want to do that is because sometimes graphs are made inaccurately, they're difficult to read, so we always want to go back and check algebraically, verifying that solution by inserting or substituting those x and y values right into that equation, the first equation and the second equation, to make sure that indeed it satisfies both equations. So that was a problem where the graph was already done for us. So now we're on to the target that says I can solve linear systems by graphing. So what if you don't have a graph? You're going to draw upon your skills that you already have from a previous chapter on how to graph a linear function. So looking at the green equation first, we are going to start with the y-intercept. And our y-intercept is 0, 3. So we're going to start by graphing the point 0, 3. So I'm going to go up to 0, 1, 2, 3, and I'm going to plot that point in green. Okay, from that, I'm going to use the slope. The slope of that line is -2. So because it's negative, I am going to use rise over run, but it's negative, so we're going to go down 2 over 1 to the right and put another point. Down 2 over 1 to the right, put another point. And we're going to keep going in that pattern. Down 2 over 1 to the right, put another point. And I'm going to plot at least 3 or 4 points so I can get a nice straight line. Be sure to use a straight edge when you connect your line, your dots, to make a line, because those points, depending on how big you draw them, they can distort the placement of your line. So try to draw your points rather small and make sure you use a straight edge and extend that line in both directions as far as you can on the grid. I'm going to make that line green just to make it stand out and be connected to that equation. Second line is going to be purple. So we are going to start at the y-intercept here is 0, -9. And this graph goes all the way down to -10 on the y-axis, so -9 would be right here. Okay, this particular line has a slope of 4. So because it's a positive 4, we are going to rise up 4 from that y-intercept, and then over 1 to the right, and then up 4 again, over 1 to the right, and then up 4 again, over 1 to the right, and we can clearly see where that intersection point is going to be. I'm going to go ahead and connect those points with, again, a nice straight edge, trying to be as accurate as possible. To be really careful. Okay, I'm going to color my line purple to match the equation. There you go. And then I'm going to look for the intersection point. Okay, so my intersection point is this spot right here, and that particular value, or that particular point, has an x value of 2 and a y value of -1. So when I write my solution, I have to write it as an ordered pair using proper format, parentheses, negative